Measurement system capability analysis or measurement system analysis or gauge RNA study or gauge repeatability and reproducibility study. This is known in these 4 different names. We'll see a typical example and then analyze them and also explain the results. So here is a typical scenario. Let's say 20 parts are measured by these 3 operators or 3 measuring systems or 3 different scales, and each part is measured 3 different times. So I have cleaned this data for Minitab and copied it already. Then we can go to stat, quality tools, case study, crossed. So part number is the number, and then select operator, and then measurement data. Under options, you can have the lower spec, upper spec limit, let's say 65, that comes from your customer. Hit OK, and then they should produce the results. Now this I have copied in this here. So here is this results. So make it a little bit bigger. So first use has a little less use in terms of gauge RNA study. So the second table is where we're going to start explaining the gauge capability and how the gauge system is doing. So this number, for example, the variation due to the measurement system is only 7.3 or 7.4%, where the process variation or part-to-part variation is about 93%. So this is what we would like to see in a gauge study, where your gauge variation, percent of gauge variation is much lower than the process variation or part-to-part variation. Now this 7.3% is actually redistributed to these two. So this two is actually sum of that. So this, if you sum these two, it should be 7.375, and then this is again redistributed to this piece and this piece. So that's the second table, so which tells us that yes, this is a okay measurement system. And let's see what next we have. The next table uses that spec limit. So this is the gauge capability, which is precision to tolerance ratio, is calculated using 6 sigma divide by the upper spec limit minus lower spec limit. Sometimes this 6 can be changed to something else depending on the amount of precision we need. In this case, Minitab uses default 6, but you can change it if you want. So this value, this gauge capability precision to tolerance ratio, is recommended that it should be less than 0.1. Or in this case, everything is calculated in percentage, so it should be less than 10%. So as you can see here, the total gauge capability is more than 10%. So with respect to the gauge capability precision tolerance ratio, it is not doing, is not to the mark. Also, as you can see here, this piece, the repeatability piece, is not to the mark. The only reproducibility piece is just under 10%. So overall, if we look at the gauge capability precision to tolerance ratio, we can say that this is not really a good measurement system. It's close, but not good. If you look at the variation in the earlier output table, has less variation, about 7.5% from the gauge, compared to the process variation, which is 93% almost, which looks kind of okay measurement system. But looking at the capability of the gauge, if we use that same standard, less than 0.1 or less than 10%, which tells it's not really a good measurement system. Now, how to explain these graphs? As you can see here, especially these control chart graphs. As you can see, these control lines are developed using basically X bar plus 3 sigma, and then X bar minus 3 sigma lower control limit. As you can see, most of the points are going out of control, indicating that this sigma value is smaller. So gauge variation is smaller. We have seen that before. The gauge for sigma was basically the variance component for sigma is only 3.5 compared to the total variation, which is 48. So it is smaller, and that's why these points going out of control. A lot of time this could be misinterpreted by the students. I have seen before that they think it's out of control, so it's bad. But for the measurement system, going out of control is actually better for the measurement system. You can also see here that part to part variation was higher, where the gauge, the measurement system has a very low variation. So it's okay, but not to the, if we use the precision to tolerance ratio, it's not to the mark.